get started?
Yeah.
Okay, welcome everyone. It's my super pleasure to present my good friend and great researcher, Jeannette Bohg. Jeannette did her PhD at KTH Sweden with Danica Krajic, also amazing researcher. You should check her out if you don't know her yet. And then a postdoc at MPI and USC with Stefan Schalt, the biggest researcher in the world, probably in terms of size.
Tallest. Yeah.
Yeah, she has been doing amazing work on manipulation and robot learning, and I don't know, awards, early career work, IEEE, RAS, Sloan. I don't know, this is too long to mention. Yeah, one of the best things about Jeannette is that she is very direct, very German in some sense, which I actually like. When I moved to Stanford, I was trying to adapt to this language. Everyone was so nice, even when they are telling me no or telling me that idea is bullshit, but it was so nice. I was kind of like coming from Germany, I was like, what is this? And then Jeannette was kind of like an island of directness. Actually appreciated and could understand. So yeah, don't BS Jeannette. She's gonna cut to the cheese. And yeah, looking forward to her presentation. All right.
Thank you, Roberto. Thanks for having me as well and letting me crash your seminar. Yeah, so thanks everyone for coming. So today I want to talk a little bit about where robotics is going in this day and age of foundation models, and the addition of this vision is on how to learn from humans, just spoiler alert. So I feel like I don't really need to explain you what foundation models are, but just as a recap, just in case, the term was coined in this massive paper with all of these hundreds of authors. Somewhere there's my name also in there somewhere. And the way we coined this term there was to say like, oh, these foundation models, these are large models trained on vast quantities of data, often self-supervised, important, right? Like, so you don't need the labels. And the cool thing about them is really that they can be adapted to a wide range of downstream tasks, either by explicitly fine-tuning or even zero-shot generalization, right? Like, that's the cool and promising thing about them. And yeah, again, like, I don't think I need to explain you what they are, but you know, there's ChatGPT, there's DALL-E, taking different inputs, producing funny different outputs. Here's an ancient reference from Google from 2017, or there are even cool works from the vision community where, you know, suddenly segmentation actually works, which is nice. So all of these types of models, they also can be used in robotics as a part of maybe robotics full stack, right? Like, they can literally be plugged in there as a module. So as I already mentioned, right, you can suddenly now use a segmentation model that actually works most of the time pretty well, certainly better than anything that was before out there. You can use ChatGPT in different ways, for example, for long horizon planning now. I'm probably, many of you have used CLIP for semantic features, or use DALL-E or things like DALL-E to basically translate a goal state into an image that the robot can then maybe achieve. Or you've used things like open vocabulary object detectors like WILD, where you can detect objects that the model hasn't necessarily been trained on. Yeah, all of these things are actually models that are coming from outside of robotics, right? Like, these are models that have been developed in the computer vision community or in the NLP community, but they turn out to be really useful as plug-in modules almost in robotics as well. And thereby, they enable generalization in robotics too. And so we have used that as well, and I'm sure many of you have used that too. Do you want me to hide this screen somehow? Let me see. Sorry.
Just drag it to the corner.
Yeah, or I think I can hide floating and new controls. Yeah. Okay, perfect. Let me do that and start again. Not start again, but you know, so we've been using obviously vision language models and large language models for manipulation research, which is what I'm specializing on. So for example, we used it for long horizon planning. and plugged it in, or basically replaced the symbolic planner with a large language model. And as you probably all know, things like ChatGPT can give you arbitrary garbage sometimes, which is a problem on a robot. And so in this particular work, we looked at how can we verify that the plan that this model actually outputs is in fact useful and doable as well. We've also worked on things like this TidyBot platform that cleans up your room according to your personal preferences. And there we used a large language model to actually summarize a few example preferences from a person to kind of distill the main idea behind the preferences and then deal with objects that the robot has actually never seen before and put it in the right place. That one is a favorite with parents and children alike. We learned that. Or you can use VLMs, for example, as reward models as well. So this is another example work where we used it for, in this case, a fine-tuning approach. So again, like all of these models, all of these are examples for taking someone else's model, like computer vision or NLP, and plugging it into a robotic system. But I think one of the core problems in robotics is still that its actual core robotic functionality, sensorimotor coordination, is still far inferior to what a person can actually do. Right, so here's an example. This is now, I guess, also ancient news, but if you remember, this is like about 2 years ago. This was front news, New York Times news, basically, for normal people, like not roboticists. And this, the reason why it was making news is because of maybe this particular example here, where the robot was asked to pick up the extinct animal, and it could do the appropriate reasoning and figure out, oh, I have to pick up this plastic dinosaur. So this reasoning, that was impressive to people, especially normal people, and I think also to roboticists, that this was possible now. But I want to point to you that the actual, if you look at this video, right, that gets sped up by an unspecified amount that you can see by the movement of this LiDAR sensor here, right? And it's doing a really, really simple pick task, really. You don't even see the placing. So it's really simple still. And 2 years later, I think we definitely made progress. There are, I think there are more complex things that these types of models can do now. And they can also generalize better, but the kinds of things that they can do is basically pick and place tasks really well, maybe some folding and things like that, right? Like that's something they can do really well at this point. But we are still far away from things like this, for example. So this is a random video from YouTube showing someone repairing an iPhone. And I think it's about replacing the screen, if I remember correctly. And it's really impressive, right? Like how this person uses tools, how they're prying out things, how they're dealing with the most minuscule little screws. And this kind of precision is probably even not feasible for me. I don't know if I would be able to do this, but certainly we're far, far, far away from using a robot to do this. And I think we are still far away from even doing, not even these precision tasks, but everyday human manipulation tasks of this large variety that we've seen. So how do people want to, obviously the ambition is to go there. So people are thinking about, okay, how can we have a robotics foundation model to allow, at the very least, this, of letting a robot just go into your home and do all these tasks that you wanted to do with all of these different objects and all of these different homes. And we want these foundation models to have the same properties as the foundation models in vision and NLP. They should generalize over, preferably zero shot, I guess, over objects, environments, different embodiments as well, and especially all of these different tasks too. And I personally, I've seen evidence for this starting to work really well, this starting to work really well, even this starting to work to some extent. But this, of really doing all these different tasks, doing new actions or combinations of actions, that's still really hard at the moment. Okay, so let's just look at what a foundation model, a robotics foundation model would actually be. And so here we have this robot. This one maybe wants to pick this particular drill. And what would it need to do? It needs to take us input, sensory information at this particular moment in time. It should probably also have some instructions, right, that it's actually supposed to pick up the drill. And then it processes this in some way and uses this as input to a policy or to a controller. And this policy or controller then outputs some action commands. So here, let's say it outputs motor torques. And this then leads to the robot, of course, moving, preferably, hopefully closer to this drill. And then, the whole cycle closes and runs again. And so all of this has to run at milliseconds, at a millisecond rate, right? Like you want to make this run really fast. And so what is the robotics foundation model here? It's basically this policy, right? Like that would be the one that would be really a core robotics foundation model. Okay, so here's this definition again that we put forward in this paper, just as a reference again. But here's like one way on how to get this policy, right? Like one is to do dynamics, to get a dynamics model of some kind, right? Like it takes its input actions and past observations and then predict what the next future observations would be. And if you had a dynamics model or what is now called a world model, right? Like now people use that term. You could basically start optimizing over a sequence of actions to get the observations that finally lead you to the goal, right? So that would be the model-based way to think about a robotics foundation model. Or another way to think about it could be just directly learning the policy, right? Like where you take observations as input and some goal representation and then output actions. So you could also do that. Oh, I'm sorry, I'm always tapping on this. I'm scared to destroy something. So what's the difference to foundation models in computer vision and NLP? The difference is that you have this dependency on actions, right? So if you wanted to have a robotics foundation model, you need to have this action in your data set somehow. And that's where all the complexity starts for robotics and all the annoyance starts, because that means you have to somehow run or collect this data on a real robot or on a simulated robot if you want, but somehow you need this label. You need this label as part of of your data set. And so that is really, if you wanted to go down this route of like getting this robotics foundation model, the biggest bottleneck towards this is this lack of data. And here's like a little visualization to just drill this in a little bit more to give you an idea of what the scales actually are. So here you have a comparison and a simple bar plot of like how many data points you have in a in the area of NLP. This is just like when I constructed this slide, whatever was the biggest model at that time in terms of how many tokens it was trained on. And here's like a slightly smaller one. And it's in the order of trillions, while in the biggest data sets in robotics on one robot are like 130K episodes or 70K episodes for Droid. And this is, so this little bar is not even to scale. So it's very minuscule. And also, of course, see what I've done here. I've made like maybe a bit of a limping comparison, which is like a token is equal an episode. You could question that. You could maybe say, okay, maybe 10 tokens are like 1 episodes, right? But it's still pretty terrible, the difference in data that we have. Also, other people also make limping comparisons if you want. So this is from a slide from Kevin Black's talk at Coral last year in November. And he is from Pi0. And so he made like this comparison of like, let's say you have 238 words per minute. That's like 1.3 tokens per word. And you can kind of map this to the kind of data that you have available as well. So he kind of laid it out like this and makes a simple, like a similar argument, right? Like that Pi, for example, has 10K hours of data. Oxy, which is this OpenX embodiment data set that I mentioned briefly later, has 4K hours and so on. And this is the comparison to the other NLP data sets. And I'll also remember it's NLP versus robotics. Robotics is way harder, I would argue. I hope this doesn't offend anyone, but I think you're not just like creating sequences of words, you are actually creating actions that affect the world, and you have to run this also in a really fast loop too. Okay, so if we stick to this comparison, what you have is this, right? Like if you wanted to get someone the same amount of data in robotics to have a robotic foundation model, you have to increase the current way of us collecting data by 15 million, by a factor of 15 million. That's insane, right? So who in this, I would say this is impossible in real hardware. There are other people who argue differently, but I would say it's pretty impossible. Who here worked on Droid in this room? Did anyone collect data on Droid? Did you collect data on Droid? 40 hours? No?
100 hours.
I know, I was also on Droid, but I did not do the annoying work, I have to say. Right, so, but, okay, so actually from the students, there's no one here who, oh yeah, there's some, okay. So I would say it's pretty impossible to scale this up in this way on Droid, on the way we collected, for example, Droid, right? So this is this data set that basically has like more than 70K episodes and all of these different scenes. The point was diversity, to get bigger diversity than was available in data sets before that. And yes, data was collected at UT Austin and at Stanford and also in 11 other institutions on top of that. So this was the data set we collected, and this is how this looked like when you collected the data. This is Jimmy Wu, who's part of my lab and who was one of the leads in my group on doing this. And basically every student who wanted to be on the paper as an author had to collect 40 hours, do this 40 hours, like one full-time day of work, right? Like 5 full-time days of work. And it gets really old. So the students who've done it, I'm sure you can confirm what my students also said, which is like they burned out pretty badly, pretty quickly on this. It's very, very boring. And it's like repetitive stress injury. Just doing this was insane. But that is kind of, I don't know, like the best kind of data you can get though for training a robot model, right? But it's just not scalable, in my opinion. But what we got was like a data set of really unprecedented diversity. So here is this visualization of the different viewpoints from which the robot was actually recorded while it was using demonstrations. It also had a wrist camera, but these are the different viewpoints from which the demos were recorded. And here's a visualization of all the different end effector poses when a significant event happened, just to kind of show in comparison to the other data sets how that looked like. You see also for RT1, they had this very particular piece of furniture in which they only collected data, while Droid, again, was like moved around in different apartments, right? That's how we got this diversity as well. Here's like a visualization of the different environments in which data was collected, so it's much more diverse than the other data sets. And here are the different verbs that were actually used in, for which basically data was collected. Note that this is a log scale, and the first few actions are pick and place. It's diverse in terms of scenes and objects and all of this, but not very diverse in terms of what kind of actions are actually being done. But still, there's a lot of data, lots of different data out there, more than in other data sets. Okay, and so I don't want to actually focus on this Droid data set today. I just want to show you it's out there and people like used it to train, to basically use it to train base policies and then fine tune for other policies as well. Okay, but it's still only 70,000 episodes compared to trillions that we would maybe need. And so what do people do to, get to this factor? So one idea is to just pool different data sets together. So this was done, for example, for this OpenX embodiment data set, where 60 data sets were basically pooled together, and it gave a total of 1 million episodes in all of these different scenes and for these different tasks. So you see actually there are very different tasks, like for example, route a cable is very different from this pick and place task here, for example, or even like doing top crafts from a metal bin or something. So it's like also very diverse. But the big challenge is it's all these different embodiments. So it's actually so here's like some images of these different embodiments, including like mobile robots or fixed base robot or robots on legs. And it's not super clear how to actually have one robot that has a completely different embodiment learn from a different one. What does actually transfer there, right? Like it's a very interesting research question that also a lot of people are working on, which I will not talk about today. Here's another idea on how to increase the size. So I'm sure many of you have seen this universal manipulation interface, where basically these people have come up with a handheld robot gripper. And it is equipped with a GoPro in this particular version on the wrist. And you can basically have a person like holding these things and doing these tasks, like for example, washing the dishes. And then the robot has the same grippers and the same sensor suite and everything, and can kind of reproduce this particular task when trained on this data. So that's like more scalable, I would say, than moving around a whole droid setup, this table with the robot and all of this from apartment to apartment. Instead, you have these relatively small grippers, right? Like that makes more sense to me as well. So that's kind of like the middle ground. And then, of course, you have another way to scale up data is, sorry, I also wanted to talk about what are the challenges with this. First of all, it's still heavy to carry that thing. Also repetitive stress injury alert here. Then SLAM actually works pretty badly on GoPros. So that apparently is the most brittle part about this. I think this can probably be improved. But the other thing is that if you look at your hands, with this device, you basically got rid of your cool hands that can do all these things, and you made them kind of dumber by having this gripper. But what this thing didn't get rid of is your wrists. So your wrists actually are also really important. So if you look at this robot, for example, with its weird kinematics, it's a little bit covered by this plastic, but it basically has a wrist that would be equivalent to us having the elbow, right? Like so, it has to do like very strange movements to get into particular configurations. And so when this person is demonstrating, it's the first author of this paper, when he is demonstrating this, he is basically trying to not move its wrist too much, because that's going to be very hard to actually reproduce on the robot that has a wrist that is somewhere in the elbow, basically. Right? So there's still like a cross-embodiment problem here still. Was this a question?
Yeah, I was just wondering your vision for the controller that you're hoping to learn from this data set. Are you planning to learn something at the force level at 300 hertz?
Yeah, that's like an entirely different question. Okay. So this particular version doesn't even have any sense of touch or anything. It has a little bit of, the fingers are these fin ray grippers, so they have some deformability and all of this. So you can see that deformation from the camera. So maybe that gives you some proxy of how much force you actually apply, but it's not very direct. But I know that in Sharon Song's group, who is like the lead behind this work, they are looking at how to put tactile sensing on it, which I think makes sense. And then the controller that's used here, right? Like that could be like a controller that runs at a kilohertz to just servo this particular end effector positions, for example. That's what you could do. But again, like there's no tactile data in this right now, or haptic data.
Isn't this fundamentally still collecting data for the purpose of a model, as opposed to the language case where the data already existed out there? And is that like, can we really increase size 15 million?
No, I don't think so.
Okay.
So going towards the actual point of my talk. So I'm just trying to, I see you are getting the point by like this number is like really crazy. So even if you have something like this, which makes collecting this data easier, right? So how do we get there, right? Like you could use simulation, and I think it's probably going to be part of the story, but simulation has its own annoying things like sim to real gap, which seems to be not matter so much for locomotion, interestingly, but for manipulation it does. There's also way more assets that you have to even create in simulation and populate your environments for, which is super annoying. I mean, every time I do a simulation project with my students, obviously as my students actually doing it, it takes always like 3 times as long, not because the project is hard in itself, but because the simulator is annoying to use, I would claim. So I don't know, I'm not into the simulation. So, but what I find really interesting is this idea of having actually robots learn from YouTube, let's say, right? Like just like you go often online and learn how to do something from YouTube, what if robots could do this as well, right? Like there are obviously all these cool data sets out there. I see Kirsten over there, right, like with Eagle 4D, and there was Epic Kitchens before. So it would be great if we could have robots learn from these. Of course, what you have again is, you know, we have our cool wrists and our amazing hands. So how do you cross this cross-embodiment problem is still a big question. And of course, the biggest problem is different from the other options on how to increase data. Here you don't have an action sequence given to you as part of the videos, right? So you somehow have to extract what this person is doing. Obviously, you also don't have any touch. Sense of touch is also not in there, but you know, ignoring this for now, even just getting the action sequence out there is like really hard. But what is promising about it is like, there is so much more data like this out there in the world. I mean, already these data sets are far bigger than this, for sure. So that's the promise of it. I think it's like really the way to potentially scale that kind of data. Okay, so how have human video demonstrations been used before? So far, there were a few ideas, and here are just some examples, and I'm sure many of you have also done work in this space, and I'm sorry if I'm not mentioning them. I'm just kind of showing some buckets here. So one way to use human videos is, for example, to train reward functions. So that's something we have done in this work that was called Concept to Robots, where we learned a multitask or generalist policy. Here it's called manipulation concept. That's what we called it back in the day. And it takes as input a natural language instruction and the scene image, the current scene image, and then outputs basically actions by a policy. And so we used, this was all done in simulation because it was COVID, but we basically used RL to learn on how to do these particular tasks in this particular scene. And the reward function was actually a video activity classifier that was trained on human videos. In this case, it was like 20 billion something something. It was an activity classifier that then looked at videos of robots doing one of these tasks and decided like whether it actually did it or not. And the reward would basically be scaled according to the output of that classifier. And what was surprising to me, so I told my student who had this idea, like, this is never gonna work. And then he proved me wrong. And the reason why I thought it's never gonna work is because we did this in simulation, and these are simulated rendered videos as opposed to the real videos that were recorded of humans with a robot inside and all of this. So I thought like, this is never gonna work, but it actually, the reward function from this activity classifier was quite useful, not for all of the tasks, but for many of them. And we think it's because this video activity classifier looked at the whole video. So it didn't matter what the appearance was, it matters what happens in the video, right? Like what is maybe the optical flow in it or something like that. And so it provided quite a useful reward signal to, in the end, learn this generalist policy as well. And so this is how we used human data there. We trained a human activity classifier that was our reward function. So that's maybe one way on how to use human video. Another way that has been done is to take data sets like Eagle 4D, for example, and pre-train a visual representation. So it takes an image in, outputs a low-dimensional latent representation of a frame, and then these people, this was done, it's like a collaboration between Meta and Stanford. They basically then took images from a robot doing a particular task and then use it as input to a policy that outputs the next action. And so they used it then for imitation learning, right? Like they trained some imitation learning policy, but using this representation that was pre-trained on human videos. So that was another way on how to use human videos. And then the third bucket, I would claim, is one where people explicitly extract sequences of how the human hand basically moves in a scene and use that in different ways. So this is like mimic play that extracts these latent plans, basically, or this latent space that basically encodes plans, and then uses that to basically condition robot learning as well. But there are many different ways on how people have used human hands tracked in these videos and objects on how to then train a robot policy as well. So these are kind of the different ways on how I see people using human videos, and I want to today talk a little bit about some work that we very recently did in this bucket, okay, where we use a hand tracker. In this case, it's always going to be Hammer. It's this hand tracking method that works pretty well to extract human hands and then use that to train a policy in different ways. So that's what I want to talk about today, learning from human videos. And here are the three works that I want to go over. One is called Motion Tracks. I'm going to go into these details. And then these other two works we just submitted to RSS. So they are not even on arXiv, but I hope they're going to be on arXiv soon, so you can look at the details of them. And so let me just start with the first one.
Can I ask a clarification?
Yeah.
You mentioned that robots will need actions. What are the actions here? I didn't catch that.
Yeah. So maybe let me go through this work and then you will see it. But it's basically the motion of the human hand, and the end which is the end effector, and then we retarget it to a robot hand in different ways with different pros and cons. Okay, so let's talk about this first one, which is called Motion Tracks. So in this work, we basically collect human demonstrations that you see up here, and specifically track the human hand and how it's moving on like 5 key points. And then we use, then we basically apply a predictor that predicts how these key points on a robot hand are going to move to get a robot policy out, right? Okay, so the key idea that is that these motion tracks, so these movements of these key points on the robot hands on the 2D image are transferable across the human and the robot embodiment. And so what we do at test time, so I hope this answers your question actually. These are basically the actions in this particular work are these movements of the key points, or 5 key points at the same time. So at test time, we predict these motion tracks from the end effector on an RGB image. And then we assume access to 2 cameras from which we run this process of predicting these motion tracks, triangulate to get the points in 3D space. And then to move the robot, we basically solve for a rigid body transform between the current end effector and the predicted point, which can be used to find the next end effector position. Okay, so why would you use this? So I would say this is an example that is true for all of these 3 works that I'm going to talk about. But basically, what you want to do is you want to collect less data on the robot and leverage data that you collected much more easily with a person. So here you have a robot that is basically showing you a demonstration of closing a drawer to the right of its end effector. And here you have some human demos that are doing the action of closing a drawer on the left and the right of its hand. And so now if you were to only train a policy on the robot data, but you try to close a drawer on the left, it basically won't be able to do anything, right? Like, because you see it's basically biased to always go to the right instead, obviously. But if you add human data, you can basically now have the robot also close the drawer on the left, despite it never having actually collected that kind of data with the robot, right? That's the idea. Yeah.
I'm gonna ask a main question.
yeah, ask a mean question.
Do you have to do the robot?
Yes. Okay, so this is going to be, I'm going to come to this at the last work where I address this. Basically, the person has to act like a robot. Right? So in both of the two first works that I'm talking about, we basically, the person has to become a grubber, right? And we're going to I talk about how to resolve this maybe in the third work as well. That's definitely a limitation of both of the two works. Okay. But yeah, basically, even though the person becomes a robot, it's still easier to collect it with their own hands, right? Okay, so here you have now the two viewpoints of the robot. We are using basically a diffusion policy to predict these 5 points and how they're going to move in 2D on both of these left and right images. And then we do this triangulation of these points and compute the rigid body transform to understand where the robot is basically supposed to go next in 3D space. So here's another visualization of this space where we have the two states, which are these motion tracks, so the movement on the 2D image that we then resolve to the actual 60 pose of the robot by triangulation. And then we keep doing this because it's a diffusion policy, right? Like it predicts 16 time steps into the future. We execute the first 8 and then we run the diffusion policy again. So you see how this looks like. And by the way, we are also predicting when the robot is supposed to close its finger. So for the data we collect on the robot, we have like both viewpoints. From the forward kinematics, we have the end effector position projected on the camera plane, not pane, and then we also get the grasp actions very easily, right? Like we just see when the fingers are closing. But now for the human data set, we don't have these two other things, right? We assume the human is like doing the action also in that same space, but how do we get the end effector position projected onto the camera plane and the grasp actions? So sorry, for the end effector position, we basically use this work called Hammer. Here's I'm sure you heard of it, but here's the reference as well, which works pretty well, not perfect, but good enough for a person behaving like a robot. And so we use, it's a frame by frame method, so it takes like a single frame as input. It fits like the manual parameters of the spinal hand to it, and we specifically are interested in 5 key points on this hand. And then we basically get data like this, where we also then look at the opening of the fingers and whether this target object actually moved to decide whether the person is actually closing its hand or not, to label basically the gripper or not, label basically the grasping or not. Okay, so then what do we do with that now? So we basically have now robot data where we get also 5 key points using forward kinematics and hand-eye calibration. And we have this human data where we extract kind of the same representation using Hammer. One thing that is interesting is that the robot hand is actually thicker than the human hand. So we have to basically train a key point, what we call a key point retargeting network, that kind of noisifies the data, or makes basically the data from the robot look more human-like as well. That's something that we have to do. And then we train what is called your motion prediction network, but basically it's a diffusion policy that predicts then forward for all of these 5 key points, the movement over a certain time horizon h, and also whether the gripper is opening or closing. Yeah. So, and then we basically, sorry, I have my shoelaces are untied. Then we basically use this triangulation method to basically get the 60 pose. Okay, so here's some results. This is a very complex graph, but let me explain what this is. So you have the robot demos here, a number of robot demos here on the y-axis, and on the x-axis you have human demos. These 2 bars are diffusion policy in ACT used for predicting these motion tracks. And in these two bars, we only use robot demos. And what you see here in these cells is basically success rate of 20 trials. And here you have motion tracks policy, again with like this number of robot demos, number of human demos. And maybe one cell to pay attention to is that if you, if you use 45 minutes of robot demos, which corresponds to collecting 70 demos, you get the same success rate as if you only use 20 minutes of robot demos and 10 minutes of human demos, right? So far less data, far easier to collect as well. Okay, so that's the first work, and here's some things that are good with it, right? Like it can learn from humans. It can really exploit that knowledge, but you still need actually some robot data, right? Like, and the person and the human have to do the demonstration in the same space, and you do need this robot data to actually cross this appearance gap even between the human data with the hand and the skin color and all of this, and the robot actually moving that looks quite different. Yeah, so that is maybe like a disadvantage, which we addressed then in this second work that I want to talk about. So that one is special because it only uses human videos. You don't need any robot data. So that one enables this. You only need human videos. There's also, again, this paper is going to be on arXiv soon, but we basically compared to kind of all of the work that is out there. And we're one of the few that really only requires robot data. We can deal with deformable objects, and we also learn a closed loop policy as well. And so by only requiring human videos, we obviously dramatically make it easier to increase data set size and diversity. You can deploy policy zero shot on any robot capable of performing the task, and it's very simple. So we basically collect a large data set of human video demonstration for a given task in a wide range of scenes. So this is like somewhere in a Gates building at Stanford and outside in all sorts of different places. And we use these human videos and then apply a data editing strategy to each frame in the data set. So what exactly do? We extract an action from the image by estimating the hand pose. So we basically use, again, hammer and that's kind of how it looks like when we do that. And then we remove the hand by actually using in-painting. So I don't remember what in-painting model we use, but it's really good, actually. I mean, there's no artifacts here, right? It's just basically remove the hand, given a mask of the hand. And then we just render the robot that we care about, that we want to execute this policy on, into this image. Just like a virtual rendering using OpenGL or whatever, right? And using, of course, the known geometry and kinematics of this robot as well. And then we get a new data set that is edited, and it basically becomes robot videos. So here's kind of a close-up of how this looks like. And it looks pretty good. There are no artifacts on like where the hand used to be. There are sometimes artifacts, how you can see, like sometimes there are artifacts on how this object is grasped, looks kind of not realistic, or here it's kind of like flying a bit, right? So that part doesn't look super realistic because that's really hard to do. But otherwise, this looks pretty good. And it turns out we can then train an imitation learning policy. Again, we tried it with diffusion policies, but you could use anything. And deploy then this policy in some new scene doing the same task. So here we basically brought this robot outside on the lawn. We overlay a virtual robot, but turns out this is actually not super important. But anyway, it's not expensive to do that. And then run this policy. And we can deploy it zero shot to new scenes. So these are completely OOD scenes with a new surface, or like outside with sunshine instead of rain, or snow, like in Austin. And here are some in-distribution scene where the data was collected with the person actually in these particular scenes as well. And yeah, it's very successful. and a very simple way to get data by just using human videos as well. We have some experiment also, like let's say you do have some robot data actually. You can of course mix this in if you have it, and the policy gets even more accurate. But yeah, you don't necessarily need it. Okay, so that's the second work I wanted to show you real quick. Of course, it also learns from humans. You don't need any robot data. Also, something I've forgotten here, you also don't need to do the demos in the same space as in this work. But just like Roberto pointed out, the human and the robot still have to follow the same strategy, right? So the person in this work still has to become a robot, basically, in a way, in their movement. So it's kind of like becoming making the hand being a gripper. Like here, probably you see it the best. So that is still just generally pretty unsatisfying, I think. But it's still a way to scale up this data potentially, and at least train a base policy that you could fine-tune them on real robot data. Okay, but we thought like the thing about imitation learning though is that you cannot get out of what the demonstrator has demonstrated, right? Like you have to somehow cross this embodiment gap, either having the person become a robot, or doing some heuristics, basically. So in this work, we actually decided, okay, why don't we use reinforcement learning to try to have the robot actually learn with its own embodiment of what works best for its own embodiment, and use a human demo not directly to provide a trajectory from which you learn directly, but instead use it to provide a reward function and also guide exploration as well. Okay, so here what we did is like we have the human essentially provide the demo. So in this case, pouring something from this pitcher into this pot. And what we extract from this demo is, first of all, the object pose. So this is going to be an object-centric approach. We don't use RGB images anymore. We use foundation pose to basically track this object, and we use hammer again to track what the hand is doing. But we don't use the whole trajectory. We just use a pre-grasp or pre-manipulation pose to basically provide the RL method then with a way to learn more effectively. So the object trajectory we will use as a reward function for the robot that learns in simulation. And the pre-manipulation pose, we do a retargeting to the robot hand and then just use that, basically do the exploration always close to that pre-manipulation pose. And then, we also use some off-the-shelf method to actually scan the environment, to get a digital twin, and also to get a model of this object. And then basically we deploy this zero-shot sim-to-real. So we tried this on different tasks. So here's like some tasks with a pretty simple object geometry, right? Like this geometric, this just box, a snack box. Doing some extrinsic dexterity with this dexterous hand as well. We have also this task with a more irregular object. We also have this very thin object to slide on the, on the surface, and then this is actually the wrong video, but either pivot it against the box, or then also do composed tasks as well that are more long horizon. So again, from a demonstration, we use the Curie engine, that's what the method is called, to scan the object and get it into simulation as a digital twin, and load this into ISAC-GIM, and we train an RL policy with PPO and simulation. And the object pose trajectory from the human demonstration is the reward. So here you see in green, basically the pose of the object as was in the demonstration, and in gray you see the object at the current point in time, and you compute a distance between these two to basically provide a dense reward to the RL policy. And then again, the pre-manipulation pose we use to guide exploration. Basically, we always want RL to be close, or the policy to be close to that. And then for sim to real transfer, we basically do this hack called domain randomization that I'm sure you're all familiar with. We are basically randomizing things like object and table friction, object mass, inertia, object initialization, poses, also the start poses for the robot arm and so on. And all this facilitates then sim to real transfer. Yeah, okay, so then for the sim to real transfer, or at test time, we basically use foundation pose, so we keep track of the object. And then we also get proprioception from the robot, which is the state of the policy, which outputs an action. And then we use this geometric fabric controller that comes out of Dieter Fox's lab to predict joint PD targets. So that last part here, this controller takes care of a few safety constraints and like avoiding collisions and so on. And so here, yes.
See that if the action then is stop commands?
These are probably also joint PD targets. Let me see, what are these actually? No, it's actually controlled in joint space, the whole thing. So these are actually joint commands. But maybe you're right, maybe it's actually for commands. I don't know. I actually forgot about this part. I can look this up later as well. Okay, so here are some interesting examples of how this looks like. So let me actually start over again. So what I think I want you to pay attention to is how this hand is dealing with this thin plate and how it's doing like inner manipulation, right? Like, so this is like some motion that would have not been in in the demonstration that a person would have done with their own hand, right? So this is really something that this robot learned from doing basically RL. You've already seen this one. So here there are some non-prehensile and extrinsic manipulation examples, which work really reliably as well. And here's like some more of this, where the robot can basically do a long horizon task and compose pushing and pivoting this box as well. Here's again like a more complex task where it does like a long horizon motion. And here's again like an interesting thing of what it learned, right? Like it learns to clip this plate, for example, between its two fingers to lift it up as well. And by the way, most of the time it actually fails in finding the right orientation to finally put it into this dish rack here as well.
Do you have the simulation videos to see if the behavior is similar?
Yeah, the behavior is similar. Sorry, I don't have the simulation videos, but yeah, it is a similar behavior to that. And again, here, like some other things that it discovered, right? Like, so if you ever worked with the Allegro hand, you know, like the fingertips are made of rubber, so they have really high friction against the table as well. And so if it slides kind of against the table like this, it actually typically gets stuck. So it learns to use its knuckles. Again, and this is also something that you see in simulation as well. Again, this was clipping this plate between the fingers. And then it can also recover, because it was trained like from different initial conditions, right? It can recover from, if it pushes the box too far away, it can catch it again. Yeah. We also tried like directly just retargeting the full human demonstration and replaying that. And it doesn't work as well as, of course, letting the robot learn with its own embodiment.
It's painful. Is it not breaking?
It's not breaking, but we do cool down the Allegro hand with a fan that is not in these videos. So typical failure cases are like, again, like this, right? Like it can't really find the right orientation of the plate. And there's a lot of foundation pose also doesn't work super well. So there's also a lot of noise coming from actually tracking tracking the objects. Yes.
So then that would actually also tracking the pose of the object. So the pose, structure of the pose actually still rely on human demonstration. So was there any case like the robot constraint actually could not achieve the trajectory of human?
We haven't seen that. And I think, it's also because the students who worked on this know kind of what the robot can do. So I'm sure they only did motion at a certain speed, first of all, so that it can be tracked, and foundation pose can keep track of it, basically, or maybe that they know a robot can sort of do. But I don't think this is actually a too strong assumption, or that there's a lot of, that constrains you too much as a demonstrator, right? I think how you use your hand and its amazing capabilities, that is the thing that is problematic for imitating for a robot, right? Because it has a completely different hand, in this case a dexterous hand, just with 4 fingers, much larger hand and so on, right? Like that is much more problematic than what the object pose can or cannot do, I think. That's much more challenging, yeah. Okay, so I think in this work, we can still learn from humans, although we use the demonstration in a very different way, right? Like we use the object trajectory for a reward and this pre-hand manipulation pose instead of the whole demonstration. We don't need real robot data, but I do think, and importantly, now the robot can learn its own strategy, right? Like with its own body. But I still think real to sim and sim to real is still very challenging. So that's like my personal gripe with that work, basically, or what I see as a limitation. Okay, so I'm kind of out of time. It's 59. I know I talked a lot about like data collection only, which is like, oh, we need data and that's all we need to do these days. But I think there is so much more that we need to think about, once, even if we had this data already. So one is think about new policy architectures that are more data efficient, right? So here, for example, we had this work that was called Equibot, where these 2 robots can learn from demonstration, again, done by a person on an object that is a completely different appearance, scale, orientation from the object that the robot's actually manipulating. So these kinds of ideas around policy architectures are, I think, really important. And we need new methods to do lifelong learning or online fine-tuning. I think that's super important because we just will never have enough data to cover everything. We want something that the robot can learn really quickly online. All these policies that I showed, most of them only use RGB data, which is kind of weird to me. Personally, I think we should, these videos are not playing for some reason. Why are these not playing? Oh, they are playing, sorry. So I think we need like also ways to include more modalities. So this particular work uses data from a force torque sensor that is actually in your fingertips and can therefore do like fine manipulation tasks that are much more complex than the other tasks that I've shown you that are mostly pick and place tasks. So I think it's unclear how to fuse haptic data or also depth data effectively with RGB data. And also we don't have so much data of these types. And I think another thing that I noticed in my work is that we really need better robot hardware because there are so cool works also out there that are coming from mechanical engineers who are doing new hands, like this one that has like, instead of fingers, it has wheels to do in-hand manipulation, which is such a cool concept. It also has tactile sensors wrapped around these wheels. That's so cool, but there exists one of those and we had to treat it like raw eggs. Right, like so one of them, and it was going to break for sure if we collected any data with it. And so I think there's a lot of cool hardware out there that we, as CS people or CS roboticists, let's say, cannot really use because they're just not robust enough. So I recently also built this mobile manipulation platform. Here's the mobile base that is completely open source. And it can carry like all this weight, for example. And so I think it's like going in the direction of more robust hardware to actually maybe be able to collect this data and run really large scale experiments. Okay, with that, I want to close this talk. So today I focused a bit on this work towards learning from YouTube, letting robots basically learn from YouTube. And I hope you enjoyed this, and thank you for your attention. Yes.
So, in your opinion, what is what we're missing? What is the most important thing to be able to learn directly from Ego 4D data? I think you went to the last project, which is one step forward. Still in the videos, it's kind of like lean motion. It's not Ego 4D. It's not kind of like supernatural. I go there, I touch everything.
No, it still looks pretty pathetic. Yeah.
What are we missing?
Okay, a bunch of things. I think one thing that is missing is like computer vision methods are still not robust enough to work. Yes, I know. I like Hammer, for example, has like for hand tracking has like a lot of brittleness still, especially under occlusion.
Are you talking to George? He's faculty here.
Yeah. Oh, he is. Oh,
Yeah,
great.
I
Yeah.
do.
I don't know if I talk with him, and I can tell him like it's not so.
He's in your
because
schedule, but I will pass that.
Yeah. So I know that Jitendra, for example, says like consider hand tracking a soft, but I can assure you it's not. Yeah. So it's really that's like the main limiting factor for the two first works that I've shown is, and the third one is like less so because we only use one pose, but for the other two where we track the entire human hand, it's definitely Hammer for sure. It's like a major pain. And the other thing is, if you wanted to do an object-centric approach, the pose tracking also doesn't work really well. It's like super brittle. It's even more brittle than Hammer. And we try to constrain it using SAM, for example, and have lots of guardrails in there. And that's also why these students are moving so slowly in these videos, right? Because they're trying to not help foundation pose. So I think if you wanted to do that kind of style of using human videos, of really parsing it in that way, you would need better methods for that. And so I think because we are not there yet, that's why people only use RGB image plain, right? Like, and do maybe more this R3M work where they pre-train encoders and things like that. Or maybe you can learn world models, right? Like where you predict these videos, but it's still unclear to me how you use them if they're only trained on human videos on robots if you don't parse out the hand, for example. So I don't really know. So I think this is like one big thing.
Yeah.
Then I think our policy architectures, they're really bad. I mean, honestly, like again, like even though I think I told many people in this room, maybe we'll talk more with other people I meet in the afternoon about this Pi Zero model. I'm actually really impressed by it, but the motion also looks still like very pathetic, right? Like it's like this, like very robotic still. And I think we're not very creative in terms of the output of these policies, right? Like we are just outputting like a sequence of waypoints. I think people who are much closer to control in robotics have come up with way better ways on how to control a robot. And I think that's something that we have to do. And then again, like what I mentioned, yeah, so, but yeah, I think that's my thought on what holds us back from leveraging human videos, I think.
And connecting to one of the points that you mentioned,
Yeah.
what about the adaptation? You said, it's so difficult with UMI, you have to do it without moving your wrist. Even if you track perfectly the hands, even if you track perfectly the objects, that is not the strategy that the robot has to use.
Yeah.
It has to adapt it. So
Yeah, I'm wondering,
how do you do that?
okay, so yeah, I'm wondering if we can use these human videos or learn from these human videos to get a base policy that we then maybe online adapt. Or so I think even if we manage to parse all these videos and all of this, yes, we will have this cross embodiment problem. So we still need robot data to do anything with that, to make it more precise. But maybe there are ways to either fine-tune with a smaller robot data set. I think that's still open on how to do this effectively, or to do online adaptation as well. Through RL, for example, and then it could learn with its own body. Yeah.
We have a couple of questions. Let's do 2 questions because
Yeah.
we're already.
Real
Sure,
quick,
sorry.
it's on the same theme, so even if you're using video data and positions, could you also try to sort of, track like minimum jerk trajectory? We know that humans do, right? As opposed to trajectories of position, you're tracking
I think we should.
trajectories of velocities.
Yeah.
Jerk, that kind of thing. I feel like policy is the same if the states are.
Yeah. Yes, we should. Yes. That was easy. I don't know how, but I think people they just take like what we have right now. Oh, it's waypoint, yeah, let's do that. But they kind of miss out on what we could do if we had better action representations, smoother trajectories, maybe controlling velocities or torque. Yeah.
So going back to the top then, this is sort of an alternative, you presented this as an alternative to the foundation model approach of like, sort of gathering tons of data and doing pixels to torques. Is it gonna get like, is it one or the other? Is there a way to combine them? Is it like, where do we,
Yeah,
what's gonna actually get us to the grand vision?
which is solving robotics.
Sure.
Yeah. Yeah, I mean, I don't know for sure, but my guess is it's somewhere in between, right? So, for example, I think Pi0, for example, predicts in joint space. If you predict motions at like, let's say, 10 hertz in end effector space, you still need a controller that makes this, resolves this motion for the full arm, right? Like, does like smoother motion, maybe is more reactive than a 10 hertz controller can actually be, things like that. So that's, for example, one example where I see both of these worlds coming together, right? That you have a policy give you the targets, but then you need all your robotics knowledge, right? Like to make it actually work on a real robot. So that's where I see them coming together. I think where these foundation models are really helpful is to link language to vision or to sensory input. I think that's really interesting and hard to do otherwise. The other thing that I think is really hard to do with these more modular approaches could be getting this corrective behavior, right? So, for example, if you have a robot that grasps this bottle, because of all sorts of errors that are showing up in your kinematic chain and your hand-eye calibration, all of this, there's always going to be an error and there's going to be premature contact, and it's really hard to deal with these types of failure cases almost, but or these very contact-rich manipulations. And I think what I think is really promising in these end-to-end policies is that they have this behavior embedded, which I think is really good because that's hard to model, basically. But yeah, what exactly will stay and what will be replaced, I don't really know.
I mean, 'cause we were talking a little last night, but
Yeah.
we're skeptical, and you presented this talk skeptical of the foundation model, but now, you expressed some sort of conversion a little bit.
Yeah.
So how do you react, or like, how do you
Yeah.
incorporate that?
Yeah. So just a little bit of background. So last week we tried in my lab the Pi0 model. And I'm personally very skeptical of seeing any videos and believing that it actually works. But this was like taking this Pi0 model, putting it on our robot that was a Franca robot that the model knows about, but in a different environment than the Droid platform, for example, different objects, cameras that were mounted for the RSS project of my student, not at all for the Pi0 model. And there were lots of people standing around it. There was no clean backgrounds. And it could do pick and place task, stacking task, insertion task, low precision. It could do folding of things. Again, all with objects that it hadn't seen. And it got like as input natural language instruction. And then, of course, we adversarially tested it. So it's easy to break still with like more complex tasks. But personally, I was very impressed for the first time. So, and so.
How do you reconcile that?
Yeah, how do I reconcile this? Well, first of all, I'm proposing yes, we need data. And how do we scale up this data? By letting robots learn from humans directly without all these contraptions and all of this, right? So you can at least get like a base policy that, but then we still need better policy architectures, better action outputs. We need online adaptation methods. And if you do learn, for example, in the N effector space, you will need all these controllers that you learned about in your Intro to Robotics class, for example. Yeah, that's kind of how I'm reconciling this actually. And I think these methods, they don't know how to take depth into account. I think there are lots of questions about why depth, if you input depth into these models, why it doesn't work better. So that's like one question. How do you get detector a sense of touch in it? Because I think that will enable these kind of fine manipulation tasks that I showed at the very end as a sneak peek of one of the works. Yeah, so these are kind of the areas. Oh, and personally, I haven't talked at all about mobile manipulation, which I find really exciting. And we built this mobile manipulation platform that is cheap and open source. And I'm hoping to actually have a fleet of robots doing things together and collaborating. That's kind of where I would love to go at some point. Yeah. There was like one more question over here.
Matt?
So I know in a lot of video data sets, there's like blur in all the frames, like pretty much all the frames.
Yeah.
And I think a lot of the data sets you showed, like they don't, or at least when you're collecting data, they don't have this blur.
No, it's a static camera, yeah, for
So
sure.
I'm curious, like how you, or not even just static camera, but if something is moving quickly, you have that blur. Like
That's
how
true.
do you deal with uncertainty in the action itself? Or how do you envision that?
Yeah, very good question. So first of all, so in this paper for this middle work, right, like where we do this in-painting, let me go back to this work. Sorry. Right, like this work where we did the in-painting, we then trained on this new edited data, we trained the policy. And we compared this policy that was trained on this edited data with data that was actually collected from the real robot. And we wanted to know if there is a difference in performance, and there was. So the policy that was trained on the robot data was actually more successful on average than, not by a ton, but definitely significantly. It was significant in the experiments than this. And the reason is because there is some noise here. Right? And so motion blur, for example, will also introduce this kind of noise in this data. So that's why I'm thinking, like, if we learn from videos, my current thought is that it will probably be good enough to have a base policy that kind of like understands like what you're trying to do, but it's not precise enough to actually achieve it. And therefore, you probably still need some robot data to, in the end, like get it to the precision that you want. That's what I'm thinking. But by having this large data sets, you can get the diversity in there on objects, on environments, on on instructions and tasks that would be very hard to get if you have to collect everything on a robot. Yeah, that's kind of where I see this going. Yeah. Okay.
Let's thank Jeannette again.
Thank you.